In this example, we have data about global warming. So we're looking at how the global temperature has increased over time. And so we have two variables. One is time and one is temperature. At least it's related to temperature. But it's measured in a sort of strange way. The way that climate scientists will look at the temperature change on Earth is by measuring what's called the anomaly, which is the difference between the current temperature and the average over some extended period of time. And so in this case here, the base period, what we're comparing to is what the average global temperature was from 1901 to 2000. So over that period, the global average temperature was at a certain level. If the temperature today is higher than that, then that's a positive anomaly. If the temperature is below that, that would be a negative anomaly. And the reason why we look at that is because we care about the change. We care about the difference between what's normal. To identify global warming, we have to identify first what is normal, and then we can say what's abnormal. And so the anomaly is essentially measuring what's abnormal. So that's our proxy for temperature in this case. So on the y-axis of this graph, we have the temperature anomaly, and then on the x-axis we have the year. And as you can see, the temperature has grown. So starting out in like the 1960s, the temperature anomaly was right around 0, and then it has grown over time. Currently, we're about 1.4-ish degrees Celsius above the 1901 to 2000 mean value. So what we're learning about is making correlation analyses. And to do that, you have two quantitative variables. You have a line, an equation for a line that defines the relationship between those two variables. And in Excel, we can ask it to give us the equation for the line and also a value called the correlation, or actually it's the correlation squared. And all of that information can be printed out here on the graph. So before I get into what this all means, let's just take a look at what where the graph comes from. So here are the graphs that we'll see, and they come from this data here. Later I'll get to what's in column B. This is carbon dioxide level, so we'll come back to this. But right now we're looking at year and anomaly. So we have two columns of data. And essentially, all you need to do to visualize the relationship between them and see if there is a correlation is to make a scatter plot. So I go to Insert and then choose this scatter plot option. We have a number of choices within here, but that's just how it's displayed. So this will be the dots by itself, and almost always that's the one I pick. This one will connect the dots with smooth lines. This one will connect them with smooth lines and then just show you the lines and not the dots. This one will connect the dots with straight lines, and then this one will connect them with straight lines and then remove the dots. So we don't care about these visualizations. We just want to see the dots themselves to start. And so you get the plot, and then you want to see the equation that best fits this trend. So if I right-click, or on my Mac I can control-click, you can bring up a menu where you can add trend line. So I add trend line, and then that will automatically bring up this other menu where you can choose the parameters that are for that trend. So first of all, you don't have to pick a linear, although that's all that we're going to be looking at in this course. The default will be linear. But if you had other reasons to suspect that this data was taking a different shape, you can choose other of these options. You can also forecast the line forwards and backwards. So that would be a kind of extrapolation of this line forwards or backwards. By default, Excel will plot the line from where the first point is located to the last point. If you want it to go further than that, you have to forecast it. If you want it to go back in time further, you'd have to go backward. Setting intercept means you can choose where this line crosses the the y-axis. So if I set intercept, the default option is 0, but you can change that to whatever you want. You'll see I don't get a very good fit, because what I'm forcing to happen is that the intercept is 0, and that doesn't work well with this data. So I don't want to choose that. And most often you don't. You want to let the intercept vary. Otherwise, it forces the line to go through the point 0, 0. And if we're looking here at the times, so the years, it starts in 1950. Let me make this a little bit bigger. And so it's easier to read on the screen. We'll increase the font size. So if I'm, click back on the line there. If I am starting here at 1950 and I do set intercept to 0, that means it's going to make this line, which looks like on your screen probably just a horizontal line. It's just a very low slope, because it has to extend back so that when this axis goes to 0, when the x-axis goes to 0, this line crosses at 0, 0, which is way, way back to the, would be way, way back to the left. We don't want that option, so we're going to take that away. Okay. We do want to see the equation for the line, and we do want to display the r-squared value. So if I check both those boxes, I get those values. Okay, and you'll see that's the same as the one that I had on the slide. The parameters of the line should be the same as what were on the slide. We're on this graph right here, except I've rounded the values, so you'll see the slope as 0.02 instead of 0.0173, but it's the same. It's the same line. So that's how you make these graphs, and then you can do other things like changing the shape of the dots and color and little formatting features. Okay, so it is fairly simple to get the information about the line, and then we can think about what to do with that information. Okay, so according to Excel, the intercept is negative 34.07, the slope is 0.02, and then this r-squared value, which is the correlation squared, is also known as the coefficient of determination. That's a 0.87. So we can say that there is a strong positive correlation here. So as time goes on, 87% of the variation in temperature anomaly is explained by this linear relationship here. So we can interpret the correlation squared, the coefficient of determination, as like the proportion of the variation that is accounted for by that relationship. And there is some scattering, so it's not perfect. It's not going to be a 1, but it's large enough that most 87% of that variation is counted for by making this line here. Now, an important point is that a strong correlation does not mean necessarily that there's a cause and effect. And that should be somewhat obvious here, because time by itself is not causing the temperature to rise. There's a third factor here, a lurking variable, like we talked about in week 1. And that lurking variable, in this case, is CO2 emissions, because over time, CO2 emissions go up, and as CO2 emissions go up, the anomaly goes up, because there's a direct cause and effect between carbon dioxide and how much heat the atmosphere retains. So the correlation that we have here is not necessarily cause and effect, but it does give us a predictive equation. And so we can use it to make predictions like what will the temperature anomaly be in the year 2050. So this is years, so we can just plug in 2050 for X. In that equation, that tells us that the temperature anomaly will be about 7. So 7 degrees Celsius rise by 2050 if the trend continues on this same path. We can ask questions about when it will reach a certain level as well. So this first question was, what will the anomaly be in year 2050? This one is, when will it be a certain temperature anomaly? So just plugging in for Y instead of plugging in for X. So when will the temperature anomaly go all the way to 10 degrees? Well, we solve this equation for x, do the algebra, so add 34.07 to both sides, divide by 0.02, you get the year 2203.5. So that's when it would reach 10 degrees. So we can use the equations to make predictions about either the x or the y variable. Plug in one and you can find the other. Now, we've talked about this, what the correlation could be, what could it mean? It could either just be a coincidence or a common underlying cause or a cause and effect. And in this case, we know that there's a common underlying cause. If it's just a coincidence, however, then that correlation we get should not be significantly different from zero. So if it just happened by chance that we find a correlation, we could look at that through a hypothesis test. And the hypothesis test is that the correlation value is going to be zero. Or the null hypothesis that we would test is that the correlation would be zero. And then if we find a statistically significant difference, we can say that there is actually a correlation there. It just didn't happen by coincidence. So we can use our hypothesis testing on this particular parameter. The population correlation is called, it looks like a P, but that's the Greek letter rho, R-H-O. That's what we're calling the population correlation. So we say that's zero. The alternative is that it's not zero. And then there's a T statistic, a T score, that involves the correlation and the sample size. So if you plug those values in, you can get a T score and then use the T distribution to find the probability that this null hypothesis is true. So in the case of this data here, our R squared value is 0.87. So if we take the square root of that, we can plug that in for T. For the formula for T, and that's 0.93. The number of data points here, although you're not going to count them this quickly, but there are 64 data points here, and we do 64 minus 2 in this case. And then again, the R squared value goes in here. So we plug all that in and we get a t-score of 20, which, as you know, is very high. And then if you looked up in Excel, did t-dot distribution to find the probability, the p-value, you'd find that that's essentially 0. So there is no chance you would get a correlation that looks like this and a correlation value this high if the true correlation between these two variables was 0. Okay, so that means that there's something else going on here, and as we know, it's a common underlying cause. It's CO2 level. As time goes up, the CO2 level goes up, and so that's the factor that that's related to both of these variables. And so the last thing I did was to actually plot temperature anomaly and CO2, go to the actual primary relationship, and you'll see it looks very similar, right? So the correlation is even a little bit higher, which is a good sign. So when you went from the variable that was correlated but not cause and effect to the variable that is cause and effect, that correlation should become even stronger, and it does get even stronger. And so here we can predict from this equation what the temperature anomaly would be given whatever the CO2 level is in the atmosphere. And that's our analysis, our correlation analysis. The process is roughly the same every time. You take your quantitative variables, make a scatter plot, find the equation and parameters of a line, this information here, and then assess whether it's cause and effect. Look for the p-value in this correlation to see if there's a chance it could just be a coincidence. And then the analysis from that point on is somewhat subjective, where you're trying to figure out could this X cause this Y to change? Is it a real cause and effect relationship, or is there, like in this case, a lurking variable?